In the last lecture, we introduced the formula for gravitational force as well as the formula for gravitational field strength. Today, we are going to focus more on the gravitational field strength and also introduce the idea of gravitational potential. First, the gravitational field strength. The formula that we presented last lecture, G equals to gm over r squared, applies for any point that is outside the Earth. And we have emphasized that G is proportional to 1 over r squared for points outside the Earth. What if the point lie within the Earth? Okay, so Newton has proven that for a point that lies within the Earth, only the mass in the dark shaded region will attract mass m, whereas any mass that is further than r1 will contribute, will have a net contribution of 0, okay, to the gravitational field strength at r1. So using this result, we can write down the gravitational field strength at a point that is within the Earth. The way to do that is to express the mass in the dark shaded region as the product of density and volume. We assume that the Earth has a uniform density of rho, and then we express the volume of the shaded region as 4/3 pi r cubed. And we can simplify the expression to an expression that has G proportional to R. This is an interesting result because it shows that the gravitational field strength increases linearly with R as you move from the center of the Earth to the surface of the Earth, with a maximum of 9.81 at the surface of the Earth. Then when you move beyond the surface of the Earth, it decreases as 1 over r squared, as we learned in the last lecture. One interesting thought experiment that we can do with this result is to imagine drilling a long hole from one side of the Earth to the other side of the Earth. And if we were to drop an object through this hole, it is possible to make use of the result to calculate the time taken to go from one side to the other side. I'll leave this as an exercise for those who are enthusiastic about finding out more about this topic. Right? The interesting thing here is that at the center point, G is 0. But of course, the person will still fall through this point because of the inertia, right? He's already moving at a certain velocity, so his inertia will carry him through this point towards the other side. You should be able to get 38 minutes as your answer. Okay, we are also going to explore more about gravitational field lines. Right, so the gravitational field lines, there are two things about the gravitational field lines. One is the direction, and in this case, it's acting towards the mass, right? And also, it indicates how strong or how weak the force is. So a point mass of the spherical mass of big M sets up a radial field, right? As you can see, the arrows point towards the center of capital M, right? And that indicates the direction of the force on a small test mass, M, okay? What about the magnitude of the force? If you were to zoom in on the field lines, right? In this diagram, you can see lots of field lines. Regions whereby the field lines are closer together, for example, near the surface of the Earth, The G field is stronger here as compared to regions that are further away, right? So the G field is actually weaker when the field lines are further apart. So by drawing the gravitational field lines, it will let us see the direction of the G field as well as the magnitude of the G field. Now, if you were to zoom in on this region here in the green box, that is region that is very, very close to the surface of the Earth, what do we notice? We notice that the field lines can be treated as almost parallel and equally spaced. Parallel and equally spaced field lines indicate an uniform gravitational field. And this is also why we have been using G equals to 9.81 meter per second squared all the time when we do experiments or when we do calculations near the surface of the Earth. One other concept that we need to be clear of when we do calculations on Earth or satellite is the difference between true weight and apparent weight. You have actually seen this idea before twice. Once in the example involving a falling leaf and a person standing in the leaf, and another time during the topic on upthrust. The difference between true weight and apparent weight lies in is can best seen in this diagram here. Right? So if you have a body that's resting on a surface, the true weight is always given by W, okay, which is actually the gravitational attraction on the mass. The apparent weight, which is what the body feels, right, is actually the force, the normal contact force that is exerted on the support or on the body by the support, right? And this N and W is not necessarily the same. They are only the same if the body does not accelerate. If the body accelerates, as you have seen in the example of the lift, N may be greater or smaller than W. So what are the factors that affect G on the surface of the Earth? First is the shape of the Earth. The Earth is non-spherical. It's a good approximation that it is a sphere, but it is not exactly spherical. So you have the distance from the poles to the center of the Earth, R1, slightly smaller than R2, which is the distance between the surface on the equator to the center. This results in a slight difference in the measured value of G at the poles compared to at the equator. The nearer the point is to the center, the larger the value of G. The second factor is the density of the Earth. It's non-uniform. If you have deposits of minerals or other substances that are of a slightly different density than the surrounding rocks, it will cause a small variation in G. This is one way that companies and oil and gas companies and minerals companies are able to detect reservoirs of minerals. Okay, the third one, which is the one of the more important factors because it involves the understanding of real and apparent weight, is due to the circular motion of the Earth. Okay, here we can apply the Newton's second law, where we can find the centripetal force exerted on an object that's resting on the equator. Okay, so the centripetal force, which is also the resultant force acting on this object, is given by F, right? F is acting towards the center, minus N, which is away from the center, right? So this resultant force here is equals to M A, okay? And we can sub in the gravitational force F and try to find what is the value of N. And as I've explained in the previous slides, N is the apparent weight and mg is the real weight. So there is a difference. In this case, the apparent weight is smaller than the real weight because of this negative mr omega squared term. We can put in the values that we know about the period of the oscillation to find the angular velocity as well as the radius of the Earth to get the measured value of g on the surface of the Earth at the equator. And the answer is 9.78, which is even smaller than the 9.81 that is commonly used in our calculations. Now the question is there a way for our apparent weight to be zero? Well, it's possible if the Earth is turning fast enough. So using this equation that we have derived previously, we can find the value of omega such that the apparent weight mg prime is zero.